In this video, we're going to take a look at a few select topics from Chapter 8, which is about sequences and series. To start with an illustration of a sequence, let's consider this scenario where day 1, there's $1, and then on day 2, $2 is added in to give a total of $3. On day 3, another $2 is added in, which makes that now 2 plus 2 added in 2 times, or 1 plus 2 times 2, which would be a total of $5. And then on day 4, another $2 is added in. Now $2 has been added in a total of 3 times. So it would be the same as 1 plus 2 times 3, or $7. If we think about going ahead to another day in the future, like day 10, now 2 will be added together how many times? In this case, it would be a total of 9 times that 2 is added together. So it would be on day 10, 1 plus 2 times 9, or a total of $19. If we consider an unspecified day, day n, then how many 2's would be added together on that day? Well, in this case, just like on day 10, there was 9 2's. Day 4, there was 3 2's added. On day 3, there were 2. It's always 1 less than the number of the day. So we'd say on day n, 2 would be added together n minus 1 times. Well, in other words, that would calculate as 1 plus 2 times n minus 1. So what we call this is an arithmetic sequence, where the same number is being added in each time. So for instance, the first one was $1, then $3, then $5, $7, all the way up to say 19, but a general formula for the nth term, we call it, is a sub n equals 1 plus 2 times n minus 1. We call d the common difference. That's what's being added in each time. We call a1 the first term, which is the number we start with. And so for any arithmetic sequence, the general nth term formula is an equals a1 plus d times n minus 1. And so in this case, the a1 is equal to 1 as the first term, and the number for d is equal to 2, since that's what's getting added in each time. So we're going to run through a few examples where we work with arithmetic sequences with different numbers for a1 and d for the first term and the common difference. Now this first one says find the first 6 terms of the arithmetic sequence in which a1 equals 6 and d equals 2. What that means is the first term, a1, is equal to 6. The second term, a2, would be 6 plus the number for d of 2. So that would be equal to 8. a3, being the third term, would be 6 plus 2 plus 2, or 10. a4, the fourth term, would be 6 plus 2 plus 2 plus 2, or 12. a5, the fifth term, would be adding 2 together now 4 times. That would equal to 14. And the sixth term, a6, would be equal to 6, and then 2 added together, in this case 5 times, which would add up to be 16. On this one it says write the formula of the general term of the arithmetic sequence to find the 20th term. Okay, on the first one it says the first term, a1, is equal to negative 70, and the common difference d is equal to negative 5. And again, the formula for the general term, or nth term, of the arithmetic sequence goes an equals a1 plus d times n minus 1. So for the numbers we have here, the nth term, an, would equal to negative 70 plus the negative 5 times n minus 1. Then the 20th term would be a20. So for a20, we're dealing with the number for n is equal to 20. And we can use the formula to plug that in and calculate for the 20th term. It would equal to negative 70 plus negative 5 times 20 minus 1. So that would equal to negative 70 minus 5 times 19. And when that calculation is done, it comes out with a negative 165. On this one, we're just given some of the numbers in the sequence, and we're supposed to figure out what to do from there. Okay, well, we look at the very first term, a1, that's equal to negative 3. And then we look at the numbers along here and how they're changing from number to number. Looks like from negative 3 to 1, and from 1 to 5, and so on, it's being adding 4 each time. So what that tells us is the common difference d is equal to that number 4. So the formula for the nth term of the sequence would go an is equal to negative 3 plus 4 times n minus 1. And the 20th term of the sequence would be a20, which would be negative 3 plus 4 times 20 minus 1. And overall, that's equal to 73. Now we consider another scenario where we start again with something here, $4. So day 1, we have $4, but on day 2, that amount is going to get doubled. So 4 times 2, or $8 total. Then on day 3, it gets doubled again. So multiplied by 2 a second time, and that would double it to $16. And so we notice how this means that it will be 2 times 2, 2 times, or 2 to the second power, 4 times 2 to the second power. And then on day 4, it'll get doubled yet again, now with 3 times 2. Now with 2 times itself 3 times, or 2 to the third power. If we go all the way forward to day 10, now how many times would we see 2 multiplied by itself? Well, if we follow the pattern, day 2 was just 1 2. On day 3 there was 2. On day 4 there were 3 2's multiplied. On day 10 there would be 9 2's multiplied together. So that would be the same as 4 times 2 to the 9th power, which is 2048. But we consider any day called day n. And since the number of times 2 gets multiplied by itself is 1 smaller than the number of the day, this would be n minus 1 times for 2 to be multiplied by itself, which would be the same as 4 times 2 to the n minus 1 power. This kind of sequence that's built by repeated multiplication by the same number is called a geometric sequence. The general term of a geometric sequence goes an equals a1 r to the n minus 1 power, where a1 is the first term and r is the thing that gets multiplied each time, called the common ratio. So in our last slide, we said the nth day calculated by 4 times 2 to the n minus 1 power. This is a geometric sequence formula where the first term is 4 and r equals 2. So we'll look at a few examples of geometric sequences and working with the formula and some of the calculations. So the first one says write the first 5 terms of the geometric sequence when we're going to look at the first one that says a1 equals 5 and r equals 3. So a1 equals the first term, That'll be 5. And then the second term will be found by multiplying by the number 3. So that'd be 5 times 3, or 15. And then the third term, we'll get that by multiplying by 3 again. That would equal to 45. And then the fourth term, again, multiplied by 3 a third time, be 135. And if we multiply to get to the fifth term, now 3 times 3 times 3 times 3. That'll be 405. And so this just continues on from here with the different numbers for different terms past the fifth term. Okay, this one's a little different. It says an equals -6 times an minus 1, where a1 is equal to -2. So the first term, a1, is equal to -2. But if we try to calculate a2, that would be -6 times a1, or -6 times -2, which would be 12. a3, it would tell us that it's -6 times a2, n minus 1. So it would be 3 minus 1, or 2, a2. So that would be -6 times 12, which is -72. a4 would be equal to -6 times a3. So that would be -6 times -72, which would turn out to be 432. Then a5 would be -6 times a4. -6 times 432. You get turning to a fairly large number now, -2,592. So that's how this sequence is defined, where we take the number for the term in the previous value. So for a2, we have to take and multiply by the a1. For 3, it would be -6 times a2, and so forth. So on this one, it says write the general term of the geometric sequence and use it to find the 8th term when a1 equals 6 and r equals 2. So the general formula for the nth term of a geometric sequence was an equals a1r to the n minus 1. So in this case, an is going to equal to the 6 for a1 times 2 raised to the n minus 1. And then it says to find the 8th term of the sequence. That means we'll be finding a8, which would be equal to 6 times 2 to the 8 minus 1, or 6 times 2 to the 7th power. Calculating that, it'll turn out to be equal to 768. On this one, it says, write the general term of the geometric sequence and use it to find the 7th term for the sequence that goes 3, 15, 75, 375, and so forth. So we notice how the very first term, the a1, is equal to 3. And then we have to look how the numbers are changing each time. To go from 3 to 15, you multiply by 5. 15 times 5 is 75. 75 times 5 is 375. So we can see how each number is a result of multiplying by 5. That tells us that r for the sequence is equal to 5. So the formula for the nth term would go an is equal to 3 times 5 to the n minus 1 power. The 7th term of the sequence would be a7, which would be 3 times 5 to the 7 minus 1 power, or 3 times 5 to the 6th power. Altogether, that would be equal to a pretty large number, 46,875. On this one, it says, write the general term of the geometric sequence and use a defined A7, the seventh term. And the sequence goes 5, -1, 1/5, -1 over 25, and so on from there. So as we can see, the first term, again, is a 5. And then we look to see how are the numbers changing from term to term in the sequence. In this case, 5 times a -1/5 would be -1. A -1 times -1/5 would be +1/5. A 1/5 times -1/5 would be -1 over 25, and so on from there. So each number generated is by the result of multiplying by -1/5. In other words, r is equal to -1/5. So the formula here for the nth term would go an is equal to 5 times -1/5 raised to the n minus 1 power. And then we'll go ahead and use that to find the seventh term of the sequence. So A7 would be equal to 5 times -1/5 to the 7 minus 1 power, or 5 times -1/5 raised to the 6th power. Okay, I went ahead and raised the fraction to the 6th power. That's equal to 1 over 15,625. So this would be the same thing as 5 over 15,625. And that reduces down to just a 1 over 3,125. So on this one, we're going to look at a few examples of applications with sequences. And this one says you're trying to choose between two jobs. One job pays a starting salary of $50,000 per year with raises of $1,000 per year. The other pays $38,000 with raises of $4,500 per year. Which would be better in 5 years? So here's how it works. For the first job, we're dealing with basically an arithmetic sequence where the first term is our starting salary of $50,000. And the D, which is what will be added each time, the raises, will be $1,000. So we can calculate this using the arithmetic sequence. For the 5th year, we'll be calculating A5, which would be equal to 50,000 plus 1,000 times 5 minus 1. And that comes out to be $54,000. For the second job, our starting salary for A1 will be $38,000. And the common difference, the thing that's added each time, is the raises of $4,500. So for the 5th year salary, it'd be calculated by taking 38,000 plus 4,500 times 5 minus 1. And that's all equal to $56,000. So we can see here which one is bigger, and after 5 years, job 2 would be better. Another one here says you're offered a job that pays $30,000 for the first year with annual increases of 5% per year in the second year. What can you expect to earn in your 6th year on the job? So we're starting at the $30,000, and the raises are yearly of 5%. The way we calculate a raise of 5% is we have to consider that the decimal for 5% is 0.05. If we start with year 1, that would be the $30,000 starting salary. But for year 2, we're going to have the $30,000 plus the additional 5% raise. We can calculate the salary after the raise has been added in by multiplying by 1.05. So that would be equal to $31,500. So again, the idea here is to multiply by 1.05 because that adds in the additional 5% raise. But we can even go further to say year 3. In that case, we would take like a $30,000. We had to multiply by this much to get the second year. We multiply by 1.05 again, and that'll come out to be the third-year salary with 2 raises added in. $33,075 would be what that's equal to. So this basically turns into what we consider a geometric sequence formula, where the first one, A1, is 30,000, and R would be equal to 1.05. So the formula then we can use to calculate the salary for any year would be 30,000 times 1.05 raised to the n minus 1. And it asked for what it would be in the 6th year. At this rate, we can calculate that by 30,000 times 1.05 raised to the 6 minus 1 power. I calculated that and I rounded it off to the nearest cent to $38,288.45.